Hello to you all, and welcome to today's webinar, ASON 2.0, Driving the All-Optical Network. I'm Jacob from Huawei, and I'm happy to be joined today by 5 industry experts in the optical network field. Throughout the event, if you have any questions, feel free to submit them in the question box on the right-hand side of the screen. We'll have a short Q&A session after our speakers are finished. Joining us today, we have Christopher Jans, VP of the Optical System Competence Center in Huawei's Research Center in Canada, Italo Busi, Chief Architect of the Optical Transport Network at Huawei's European Research Center, Adrian Farrell, former Routing Area Director of the Internet Engineering Task Force, Anka Janwar, Assistant VP of Transport Network ISG from Telkom Indonesia. Let's start by handing over to Christopher Jans, who will be exploring continuous ASON evolution in the optical networking 2.0 era. Over to you, Christopher.
Thank you, Jacob, and hello, everyone. Again, my name is Christopher Jans. I'm the Director of Huawei Canada's Optical Systems Competency Center. Traditionally, the optical transport network provided what everyone tends to call dumb pipes. That is transparent data transmission carriage for service-bearing protocols, not directly touching end users, without visible or guaranteed network latency, and with limited or no performance analysis or automation support. Next slide, please. 2 years ago, Huawei introduced the Optical Networking 2.0 solution, which focuses on providing lower per bit total cost of ownership through technology innovations for single fiber, single site, and improved operations and maintenance, and premium experience for high-value end users to allow providers to tackle new business opportunities. Next slide. This is what we call the 5S tree of ON 2.0. New premium services are on the top of the tree, including OTN-based premium video services for live broadcasts and video on demand, OTN-based 5G backhaul, and OTN-based private line services for finance, government, healthcare, research, manufacturing, and other large enterprise sectors. According to statistics from one major Chinese operator, the number of OTN-based premium private lines today accounts for only 3.7% of all their private line services. However, they account for 37% of revenues and 52% of profits. OTN-based premium private line services repose on a new architecture based on OTN Everywhere and a rich mesh based on optical cross-connect ROADM Everywhere, yielding a 3D, flattened, one-hop connection, OTN service-capable optical network. That's new schema. The roots of the ON 2.0 tree relate to technical innovations. We continuously reduce effective TCO per fiber by increasing channel rates from 100 gig to 400 gig. That's new speed. We continuously reduce effective TCO per site with optoelectronic convergence, reducing footprint and power consumption of equipment. That's new sites. And we continuously reduce OpEx of operations and maintenance with edge and centralized intelligence and end-to-end automation on O&M. That's new smart O&M. Next slide, please. Traditional ASON offers 2 key functions. First, automation, which helps WDM OTN transmission devices implement automated provisioning functions, including automatic device discovery and automated service connection. And second, protection, providing network level protection against multiple fiber cuts for carriers, and 5-level SLA protection to satisfy refined service operation requirements. Premium new services make the transformation of optical networks from dumb pipes to service providers. to service networks. Simplified new schema means OTN to CO, OTN, and optical cross-connect everywhere. We need speedy recovery to make guaranteed high service availability for high-value new services. We need scalable network to make OTN to the CO, so to break through the existing network scale and converge the backbone and metro OTN networks. And we need smart network. Ultimately, the AI-based digitization of optical network is the only way to support true automation of the network. My colleague Italo will give a detailed speech on ASON 2.0 solution.
Thanks for that, Christopher. Now let's turn to Italo Bussi, who I believe is going to introduce ASON 2.0 and explain some of the core technologies involved. Italo, we're ready when you are.
I'm ready. Thank you, Jacob. Thank you, Chris. So what we are going to explore a little bit more in detail the three S's that Chris has introduced as the key features for ASON 2.0. So the network is becoming more smart, speedy, and scalable. Why we need smart network? The reason is that with ASON 1.0, the modeling for the optical layer is analog. It's a complex modeling, analog, and we have a feedback-based commissioning, which takes long time to commission new services, and also in order to adjust the optical power amplification, we have to manage high margin to avoid to have the nonlinearity effects which affects the performances. The evolution with ASON 2.0 will enable using more digital AI and machine learning data modeling, which is a smart way so the smart concept for modeling the optical layer. We can monitor the behavior of the network, and we can predict the performances of the network, and have a more faster commissioning, and to have low margin, so have a more efficient use of the spectrum on the network. Speedy recovery means that with ASON 2.0 we are going to improve the speed of recovery in case of a fiber cut from minutes to seconds in the optical layer, and from seconds to 100 milliseconds in the electrical layer. And scalability means that the network, if OTN and optical network is going to widespread deployment to be deployed in large scale, the ASON 1.0 scalability is not enough, because at this moment in time we have a limitation of 400 nodes in the electrical layer and 150 ROADMs in the optical layer. If you build a bigger network, you want to have a single ASON domain that scales for large countries and metro networks, covering both backbone and metro networks. We have to increase at least to 3,000 nodes in the optical layer and 1,000 nodes in the ROADM. Next slide, please. So we can see how the smart approach, the approach for network planning and commissioning smarter means that we have to take into account the complexity of the physics. The optical network is a very dynamic system which varies as a fast time reaction. So we need to adapt to this dynamicity of the network. The signals that propagate through the network are analog signals. So they are unstructured data with nonlinear and coupling effects, which make it difficult to model the behavior and predict the behavior of the system. And in order to optimize the network, you need to take into account a huge amount of states and parameters, and optimize a multidimensional system is not that easy. The current approach is based on a feedback control approach with analog modeling of the network. Takes long time to converge on one side, and on the second side, on the other side, it takes also requires high margin, because the error can be too big, and you don't want to disrupt your network if you make mistakes. The new approach is taking advantage of the evolution of the technology with AI and machine learning. So the idea is to have To collect big data, what does it mean collecting big data? Collect more information in terms of sensor, having more optical sensor in the 4 dimensions, having sensing the performance of the service, of the channel, on the component, and on the fiber, and to collect them very quickly every second, so you can adapt with the dynamicity of the system. And then you can use this information as a training for machine learning modeling that can predict the behavior of the system or what is going to happen in the system. This will make much faster provisioning, a lower margin, and a more reactive network. Next slide, please. And based on that, we can also have some improvement in the architecture of the ASON support, have some hardware acceleration on the control plane, and to enable faster rerouting. So the target is to reduce the rerouting in the electrical layer, which from seconds to few milliseconds, few hundred milliseconds, 200 milliseconds, with 50 milliseconds being the target, which means that every failure will have basically zero impact on the service availability. And for the optical layer, the optical layer recovery is a little bit slower because of the nature of the signal, but we try to go down for minutes to seconds. Around 10 seconds is the target for this year, hoping to go even below 2 seconds to avoid impacting the routing IP network flapping. And the advantage of all this capability is that we have a system which is more resilient against the failures. You can offer premium services with higher reliability and monetize, and therefore have different service level agreements with different operators and have more revenue opportunities. Next slide, please. The third dimension is the scalability. As I said, if you want to deploy optical network through the optical devices through all the network, then you cannot put all your systems into a single backbone. You have to go and scale down to the metro access and metro aggregation. And so this means that the number of network elements that you need to control is increasing. And then you need to improve the scalability of the ASON domain from 800 electrical network element and 150 ROADM towards more than 3,000 electrical network elements and 1,000 ROADM. And to do that, the idea is that the ASON domain can be divided into a multi-area solution, IGP, and allow to set up scalable services across different areas. To do that, we should simplify the architecture, so having multiple areas, so divide the network into ROADMs into different areas, and to simplify the protocol, for example, get advantage of some hardware scalability, hardware acceleration to have more performances in the forwarding and state, and have more smart algorithms to reduce the number of paths that you have to attend to set up when there is a failure. Next slide, please. In addition to these three evolutions, we have also to ASON 2.0 needs to take care and be able to support the latest data plane evolutions, which are coming with the optical network 2.0 that was also introduced by Chris. As Huawei, we are introducing new devices, both in the electrical and the optical layer, like the optical cross connect and the M1 and M12 and M24 optical devices, as well as OTN cluster for the electrical layer. And ASON 2.0 should support the control of these new devices. Plus, we have a new tributary rates, 200 and 400 gigabit client signals to be supported over WDM networks, as well as the higher speed line rate, like 200 and 400 gigabit lambdas. Plus, we have evolutions in the data plane, in the spectrum optimization. So in order to put more bits on the wire, we are evolving from a standard C-band to a larger super C-band that will allow having more lambdas over the same fiber, as well as using the flexible grid capabilities to slice the spectrum into smaller pieces and have more efficient usage and filling the optical signals over the fiber. In addition to that, Liquid OTN is also introducing flexible ARP pipes, which also needs to be set up and controlled by ASON control plane. So these three S's plus the new evolution of data plane capabilities will be the key pillars from the ASON 2.0 control plane evolution. Thank you, Jacob.
Thanks, Italo. Let's move on and welcome Adrian Farrell, who's going to discuss the ASON standards prospect of the IETF. Adrian, over to you. Sorry, Adrian, to interrupt. I'll just unmute you. Sorry about that. Please continue.
Thank you. Yes, so I'm a consultant specializing in internet and transport protocols. So I'm going to talk a little bit about the history and the future of generalized multi-protocol label switching and ASON standardization. Next slide, please. So when we look at the history, we can trace back to the mid-1990s when some of the TDM technologies were being developed and were chiefly provisioned using management systems. And that, as that was going on, ATM was also developed with management protocols and then control plane protocols being introduced. And before long, the IETF became involved with multi-protocol label switching, MPLS, using an IP-based control plane. And the first RFCs, those are IETF standards, came out for MPLS traffic engineering in about 2001. And as that work was going on, people started to realize that the connection-oriented nature of MPLS traffic engineering was very similar to what you had in optical networks. And the idea of MP lambda switching was invented to reuse a lot of the work for MPLS TE. Quickly, people said, well, don't just limit yourself to lambdas. You should be able to do this for all types of transport switching. And this was converted then to generalized multi-protocol label switching, GMPLS, covering all sorts of technologies. And the first specifications for that started to come out in 2003. So next slide. What GMPLS is a family of control plane protocols. There are three main areas of functionality that GMPLS covers. The link management protocol, LMP, is used just between adjacent nodes to discover the capabilities of the links, to make sure that ports are plugged into the right partner port, and to monitor the status of the link. And then there's connectivity and resource availability advertisement, which is very similar to what exists in IP networks, and extensions were made both to OSPF and ISIS to convey GMPLS traffic engineering information throughout the network, so that you've got a complete network-wide view of the topology. And then a signaling protocol for connection establishment and maintenance was developed, called RSVP traffic engineering. That was based on the old RSVP protocol, but really not related, because the old protocol was very soft state, very packet based. RSVP TE is a much harder state protocol and is connection oriented. There was a blind alley called CRLDP that was invented for a while and then was put on one side. So now GMPLS is just RSVP TE signaling. All of this became standardized around 2003. Somewhat later, and 6 years later, we discovered we could benefit with offloading some of the path computation functions, some of the determination of what route through a network to signal. We offloaded that to a component called the path computation element and developed a protocol for that called PSEP. At the same time, there were various generalizations and extensions being developed to support more and more data planes and the bandwidth and resource identifiers needed for those data planes, and to support the popular features of circuit switching like bidirectionality and fault reporting. Next slide, please. So as this was happening at roughly the same time, the ITU, Telecoms Division, ITUT, was developing a series of recommendations for the automatically switched optical network, which they called ASON. So this was, in the context of this webinar, this was ASON 1.0. Of course, it wasn't called 1.0 because there was no plan for a 2.0. So we just call it ASON. This is very strongly driven by architectural principles. So breaking things up with clear interfaces and hierarchical decomposition of the network, and a discussion of abstract messages and control. And that then led into a little bit of tension between the ITU and the IETF, because there was a clear overlap between some of the work being done, with the ITU wanting to lead on architecture and the IETF wanting to lead on protocols, and some different terminology that developed in the two organizations that added to the tension. But through a degree of cooperation and sharing and discussion, things moved forward quite nicely. Next slide. So over time, GMPLS protocol suite became enhanced. Many extensions were applicable both to MPLS traffic engineering and to the more traditional transport networks, but some were only specific to data planes. And to give you an idea of the scope of this, there are 108 standards coming out of the CCAMP working group that's responsible for the GMPLS pieces that are related to data planes. So a lot of that work is adding new support for new data planes, and a lot of it is for management of the protocols and the data planes. Next slide, please. So what are we working on at the moment and where are we going? GMPLS is still being developed, being enhanced within the IETF. A lot of the core work, of course, is done and implemented and deployed. There are 3 working groups active in this. The CCAMP working group is very much technology specific, and they are looking at the moment at B100G, at optical impairments, media channel, subcarriers, and there will be more. As more data planes are invented or is extended, there'll be more protocol work. And of course, there are Yang models. Everybody's writing Yang models these days, and CCAMP has got plenty. The TEAS working group is the Traffic Engineering and Architecture and Signaling working group. And it tries to do architectural considerations. So it's looking at abstraction and control of traffic engineered networks, network slicing, and SDN. And it also looks at generic protocol extensions, those that are applied to MPLS, TE, and GMPLS. And of course, Yang models. And then the PCE working group looks specific extensions to PSEP, and there's some of those for GMPLS. Now, where this might go in the future, I think is quite interesting, because we're now looking in the context of ASON 2.0 at how could GMPLS be improved to deliver better functionality. So support for larger networks, where we're currently very limited by the IGPs and what they do. Faster connection recovery, where we're currently limited by detection, reporting, and propagation of issues by the convergence of the IGP, and then very importantly by resignaling. And then lastly, smarter integration with users and applications to handle their network attributes. So that's me. Thank you very much, and we'll see how that fits in.
Great. Thanks, Adrian. Let's turn to Anka Janwar, who can share some of Telkom Indonesia's unique experiences in the optical network field. Anka, whenever you're ready.
Thank you, Jacob. Hello, everyone. My name is Anka Janwar from Telkom Indonesia. Currently, in charge of Telkom Transport Network Solution Strategy and Governance. I would like to take this webinar as an opportunity to share the ASON application in Telkom network, especially in Java backbone network. Next, please. Firstly, I'd like to take 1 minute to introduce a little bit about Indonesia and Telkom Indonesia. Indonesia is a country in Southeast Asia and Oceania, between the Indian and Pacific Oceans. It consists of more than 17,000 islands, including Sumatra, Java, Kalimantan, Sulawesi, and New Guinea. Indonesia is the most largest island in country and the 14th largest country by land area, with over 267 million people. It is the world's fourth most populous country. Telkom Indonesia is the largest telecommunication company in Indonesia with 9.4 million fixed line subscribers, around 170 million mobile subscribers, around 2,000 corporate customers, and nearly 300,000 small and medium-sized enterprise customers. In order to support the innovation of its digital services, Telkom carries the mission to develop and maintain an agile and resilient network. Next, I will introduce the ASON journey to build agile and resilient network. Next slide, please. As we all know that fiber is the key for the service availability, and 57% of the service interruption are caused by fiber cut, which result in bad customer experience and huge revenue loss. For Telkom, fiber cut and fiber deterioration are the big challenges in the optical transport network. Since from 2018, Telkom has started to deploy ASON solution in optical network. Step 1, in 2018, we upgraded the Java backbone from static 1+1 to ASON with 99.99% availability. Step 2, in 2019 half 1, with a program called Video Centric Network, WDM network with ASON enable to ensure the great video experience in East Java. Step 3, upgrade Sumatra OTN network to ASON with higher service availability. Right now, we are at step 4. We further optimize Java backbone network with full mesh plus ASON plus NCE transport to building a further enhanced resilient network. Next, I'm going to share the ASON case of Java backbone. Next slide, please. Java, the world's most populous island, is home to more than half of country's population. Java Backbone Network is connecting the Indonesia biggest city, is a capital city to Jakarta, and the second biggest city, Surabaya. Fiber cut caused by natural disaster from instance flooding or construction is quite frequent in Java Backbone Network. For instance, there were 22 fiber cuts from January to February in 2018, results in huge loss for telecom and service interruption will cost you penalties per hour. Java backbone was built with one plus one static protection, unable to cope with multi-fiber cut, and its service availability is around 98.5%. The annual service downtime is 130 hours in 2018. So we decided to upgrade the ASON with permanent diamond 1 plus 1 to build more resilient network with 99.99% service availability, and the annual service downtime has been reduced to 0.8 hours. Next slide, please. However, challenges are still ahead in this network. First, more and more fiber cuts still ongoing. For instance, there were 169 times of fiber cut in 2 months. Second, there were no more margin for many links caused by fiber deterioration. And third, there were some working and protection roads are in the same cable due to some restriction. Last, the network still not full mesh, unable to drive ASON play its best. In 2020 half one, after detailed network assessment and planning, we decided to take 3 measures. One, build 8 new rodent sites for a more full mesh network, which will offer more roads for the protection and rerouting. Second, build 15 more OLA or repeater sites for better performance. And third, upgrade from U2000 NMS to NCE transport for management plus controller and analyzer ready network plane. We expect that full mesh plus ASON will enable a more resilient optical network. By the way, this project is in the deployment stage, and we are sure we are going to benefit a lot from this ASON network. Next slide, please. If we look at the future of the ASON, I hope ASON 2.0 can bring faster rerouting in both electrical and optical ASON. As faster rerouting, time definitely will improve service reliability. Second, into business private line domain, service availability will play a more and more important role. Higher availability will bring better user experience and higher profit. I do believe that The rich SLA of ASON and availability map from NCE Transport will bring availability as a service into ready and bring more possibilities to business private line markets. I think that is all for my ASON case sharing. Thanks a lot for your time and participation. Thank you.
Thank you very much, Anka. We're now going back to Christopher Jans to take us through an ASON network availability evaluation demo.
Thank you.
Chris, if you could please share your screen.
Indeed. Okay, you can see that, Jacob?
Yes.
Okay, very good. So as just discussed by Telkom Indonesia, service reliability or availability could be a controllable and monetizable service feature for telecom operators, just as bandwidth traditionally has been, and now also latency and fast time to market. So this is the realm of mass customized private line services, where customization is based on multiple service parameters. And we've also seen similar cases from other operators. For example, a carrier customer in China is offering different pricing for different service availabilities. Now, of course, in order to monetize committed availability, from a qualitative description to a quantitative description, a methodology and the supportive tools is necessary. We need availability evolution over a planning period, an assessment and calculation extending to a service market offer period, and monitoring and optimization tools, an O&M period. So to support this, we need effectively an availability monitoring app based on ASON. And let me walk you through quickly such a feature in iMaster NCE, Optical Availability Assurance. This is a dashboard view. It gives us a range of useful statistics. In the upper left, we see historical statistics on fiber and service availability. On the right are numbers of fibers which have had better than 5 nines availability. And as we go to each category on the left, we see the numbers of fibers and services which have had 4 nines, 3 and 2 nines historical availability. In the next two windows to the right, we have trends on fiber cuts and service interruptions. We can see historical data related to fiber and service interruptions over a 3-month period and in recent days. We can see numbers and durations and worst fibers and services, i.e. which fibers and services, with details available holding the cursor over the bars with respect to these metrics. Now, understanding of the sources and histories of fiber and service interruptions is further aided with information on the fiber and service availability tabs. For example, going to the fiber availability tab, and I hope I can do this. There we go. Sorry, it's just a little slow. Everything's going through the same internet connection. We see a map of fibers in the network. The fibers are color-coded to suggest how problematic each has been in terms of interruptions. We can get information about each fiber by holding the cursor over each fiber on the map. And there are statistics in the upper right showing us percentage of fibers in each class. On the bottom, we have various views, including a summary of fiber interruptions by date, an extended ordered histogram of interruptions by fiber, and a list of fibers with the various interruption history details. Similarly, on the service availability tab, at bottom, we have several views of statistics related to service interruptions, We can see by date the number of fiber cuts and the number of service interruptions, ASON protected, default protected, or unprotected, as well as summary views per service and interruption details per service. Now, returning to the availability dashboard, one second. Returning to the availability dashboard, we have service interruption statistics, protected versus unprotected, in both capacity interrupted and capacity duration of interruption terms. Fiber sharing risk analysis showing percentage of services with and without shared risk, shared fiber components, and service capacity duration interruption statistics with and without shared risk groups, and service protection benefit statistics. The latter tell us the protection and ASON-based rerouting counts and capacity duration statistics in various time periods. And of course, as it happens, show clearly the availability benefits of ASON-driven rerouting protection. These NCE features support detailed planning, monitoring and assurance of monetizable degrees of committed service availability planning.
Thank you very much for that, Christopher. Sorry for the pause there. I will now ask Italo to help us wrap up and summarize the content so far.
Thank you, Jacob, and thank you to all the other speakers. What I think we have done through a good journey to see how the evolution of optical network 2.0 in terms of new services, new structural architectures is driving the evolution for the ASON control plane into ASON 2.0, and in particular the three pillars, which are the optical network control plane to become smart, speedy, and scalable in terms of using AI digitalization, measure and predictable control, and increase the speeding up the routing from into milliseconds in electrical layer and seconds in optical layer, and scale the network to 300 electrical nodes and 1,000 ROADM nodes. The GMPLS standards have a strong potential to be improved to support these requirements for large network, faster acceleration, and more application awareness, so more integration with users and applications. We have seen a couple of interesting use cases, commercial use cases, and we have seen in Telecom Indonesia how ASON has been very useful to enhance the service availability and minimize the service interruption, also in case of frequent fiber cuts, avoiding huge financial losses and revenue losses thanks to this capability. And we have seen a demo from Huawei on how ASON can be a key technology to support service availability in a way which is guaranteed, and that allows to have a monetization of that by allowing different service level agreements, as well as to guarantee and ask for premium prices for services which are better protected and more available. Thank you, Jacob. Thank you, everybody.
Thanks, Italo. Now it's time for our Q&A session. If you haven't already done so, please use the chat box you can see on the right-hand side of the screen to send us your question. Anchor, can you please explain a little more how full mesh networks can unleash the full potential of ASON?
Okay, thank you, Jacob. As we know, that the ASON is to protect the service against multiple fiber cut. To ensure the minimum service interruption, only by building a full mesh network, it can provide multiple routes both for protection and rerouting. which will help provide higher service availability. Therefore, full mesh network plus ASON is the best communication. Okay, I think that's all, Pak.
Great. Thank you very much. And
Welcome.
lastly, I have a question for Adrian. Adrian, can you please elaborate the difference between MPLS-TE, MPLS-IP, and GMPLS, and why we select GMPLS for ASON?
Yeah, great question.
Sorry?
The starting point for MPLS is a packet-based system that follows the IP IGPs, and that is really best effort. What MPLS-TE does is extend some of the protocols to provide resource reservation and path planning so that there's much more predictability in the delivery of traffic, but it's still a packet-based system. GMPLS is the generalization of MPLS-TE for both packet and a variety of traditional and future transport networks. So anything from Ethernet through Lambda and port switching, TDM, OTN, anything you like, really. It's just a generalization of MPLS-TE. And then as to why we should use GMPLS for ASON, well, I think there are three fundamental things. Firstly, it works. It's shown to work, it's deployed. The second thing is that it's standardized. So there are multiple vendors implementing, and it can work interwork between those vendors. And of course, that means that there's a portability of knowledge base as well. But the third point to make is that it is only one of a possible set of solutions. So other protocols could be developed. And I think ASON 2.0 will see modifications to GMPLS and extensions and possibly some small new protocols that achieve slightly better and fine-tuned results.
Great. Thank you very much, Adrian. And finally, I have a question for Italo. So Italo, what is the main difference between ASON 2 in comparison to ASON version 1?
Well, I think the main difference will be in my opinion, the scalability, which requires to have a smarter architecture and a more so you have more data to collect and you have more data to distribute, and so you have to have some capability in order to cope with all this data, and also a bigger network. So you have to be able to restructure a little bit your protocol and implementation to cope with that scale, big numbers.
Okay, great. Thank you very much.
Thank
you everyone at home for your questions. I'm sorry if we didn't get round to answering yours live. We'll get back to you over email, rest assured. I'd like to end by thanks ever so much. Finally, thanks to all of you at home for watching. Goodbye.